But here we have to find the series, the power series expansion, right, in powers of x of all these functions here. Of course, one can always apply the definition of the Taylor series and then write this in this way. This is the derivative at the point 0 over n factorial times x to the n. This is the general form of this, but that's normally not the right way to do it, because as soon as the functions are complicated, then this becomes very difficult to calculate, right? And this is actually the case. So what we're going to do is to try to get this series in an alternative way, using non-series of functions, of some functions, right? So let's begin with the first, right? The first one here, the sine squared. Okay, we know the series of the sine. And a temptation when we see this is to use the series of the sine and square it. But squaring a series is complicated, right? It's not an easy task. So that's not a good idea. However, this is a trigonometric function, and there are many relations of trigonometric functions with other trigonometric functions. And in particular, the sine squared is equal to 1/2 1 minus the cosine of 2x, right? Now, this is a much better way of expressing the function to use a series, because what we have here is 1/2, of course, right, minus 1/2, and here we have the series of this, which is the sum from 0 to infinity minus 1 to the n over n factor over 2n factorial, right, 2n factorial, and then we have 2x to the 2n. Okay, this is the series. Remember, the series of the cosine is equal to this, the sum from 0 to infinity minus 1 to the n, x to the 2n over 2n factorial. Okay, so that is what it is, right? So we can just rewrite this a little bit. So we have 1/2 here, and then we have, let me write this correctly. So we have the sum from 0 to infinity, then we have minus 1 to the n over 2n factorial, that's okay. Then we have 2 to the 2n minus 1, so 2 to the 2n minus 1, right? And then we have x to the 2n. Okay, this way of expressing the series is a bit ugly, because we are separating a constant here, and there is another constant here for the term n equal to 0. So the nice thing to do is to put the two constants together. For that, all we have to do is to separate out the term n equal to 0. So for n equal to 0, what we have here is 1, here we have 1, here we have 1/2, and here we have 1. So actually, this is the term n equal to 0. And then we have the rest of the series, so starting at 1. Okay, and the expression of the general term is identical. So the only thing we've done here, as you see, is separate out the term n equal to 0, which is a constant. And now you can see that this is a good idea, because the constant actually cancels. So this is equal to the sum. Well, you have a minus here, but this minus can be grouped with this minus 1, and you can put here minus 1 to the n plus 1, right? Then 2n factorial in the denominator, 2 to the 2n minus 1, x to the 2n, and here you have the sum from 1, not 0, from 1 to infinity. The constant is equal to 0. Makes sense that the constant is equal to 0, because what this means is that f of 0 is equal to 0, which it is, right? F of 0 is equal to 0. You can see it here, right? So this is the expansion of the sine square, okay? Right, so let's go to the second, okay? The second is equal to this logarithm of this complicated square root, okay? Which is a bad way of trying to do the expansion. However, if you remember that the square root is just an exponent 1/2, this is actually 1/2 of the logarithm of 1 plus x over 1 minus x. And again, this is just the logarithm of a quotient, and that is the difference of logarithms. So we have this difference, which is very good because both these functions are easy to expand, right? Because we know the expansions of the logarithm. So let's do that. The logarithm of 1 plus x is equal to the sum from 1 to infinity of minus 1 to n plus 1 over n times x to the n. So if you change x by minus x, you get the logarithm of 1 minus x. And if you do that, what you get is minus 1 to the n plus 1 over n. And here you get minus 1 to the n times x to the n. So you have here minus 1 to the 2n plus 1, which is always odd, and therefore this is always negative. So this is equal to minus the sum from 1 to infinity x to the n over n. All right, we have the two expressions now. We can plug them in here, and then we have f of x is equal to 1/2 of this minus 1/2 of this, right? So 1/2 of the sum from 1 to infinity minus 1 to the n plus 1 over n, right? X to the n minus this one, minus and minus cancel, so plus 1/2 the sum from 1 to infinity x to the n over n. All right, the nice thing to do is to express this as a unique coefficient with x to the n. So we have to group these two things together, and that is very easy, because what we have to do is just factor out the x to the n here. So we have minus 1 to n plus 1 here, plus 1 divided by 2n, right? Sum of these two terms, and then x to the n. Okay, this is one way to express it, but look at this term here. So what does minus 1 to the n plus 1 looks like depending on the values of n? Well, suppose n is even. Well, suppose n is odd, right? Because we begin with 1, so we begin with odd. If n is odd, then odd plus 1 is even. So this is 1, and 1 plus 1 is 2. So we get 2. This coefficient is 2 for n odd. However, if n is even, this is negative 1 plus 1 is 0. So what this means is that none of the even terms appear in this series. They only appear the odd terms here. So we can write the sum from 0 to infinity, okay? And then we have x to the 2k plus 1, right? N is equal to 2k plus 1 here. So I'm starting at k equal to 0, because for k equal to 0 we have 1, which is the first odd power that we have here. And then the coefficient here is 2, right? Divided by 2 is 1. And we're left with n here, and n, as you see, is 2k plus 1. So you have this very nice simple expression for the expansion of this function f, right? So f looked pretty complicated when we had it written in this form, but it turns out to have a very simple power series. It just contains the odd powers, and the coefficient is just 1 over the power. That's it. All right? Okay, so that's the second one. Now the third, well, we have to specify the domain of validity of these expansions, right? Well, the case of this one, which I forgot to mention, is the domain of validity is any real value, because the series of the cosine has radius of convergence infinity, right? So it is valid for any x. However, this one here, for this one here, we're using the expansion of the logarithm, either this or this, and that is valid only when the absolute value is smaller than 1. So this one here is valid when the absolute value is smaller than 1. The radius of convergence of this is 1, right? Okay, let's go to the third. So the third one is x over a plus bx. X over a plus bx. All right, this is basically, well, factoring out appropriate terms. We can write this very similar to the geometric series. We factor x to divide by a here. So what we have here is 1 plus bx divided by a. And this is the geometric series 1 to infinity, where the argument is minus bx divided by a to the n. Okay, where does this converge? Where the absolute value of bx over a is smaller than 1, which means the absolute value of x is smaller than a over b absolute value. Okay, so this is the radius of convergence of this series here. All right, well, we can rewrite this in a better way, just separating out the constant and introducing this one here. So what we have is this: we have the sum from 1 to infinity. Okay, sorry, it's not 1, it's 0. I'm sorry. The geometric series begins at 0. All right, 0. So we multiply this, so we have, well, first we have minus 1 to the n, right? Then we have b to the n. Then we have a to the n plus 1. And we also have x to the n plus 1. Okay? And, well, the nice thing to do is to write this in powers of just n, not n plus 1. And for that, we just shift the index 1 unit up here and 1 unit down here. So we have minus 1 to the n minus 1 here. And we have bn minus 1. And here we have an. And here we have x to the n. That is the expansion. And as I said, this is the interval of convergence, right? Okay, of absolute convergence. All right. Now, this one here, 4, is 1 over 2 minus x squared. Well, it's pretty much the same as the previous one, right? What we have to do is to factor out 1/2, and then we write this as this function, which looks like the geometric series, right? So it's 1/2 the sum from 0 to infinity x squared half to the power n. That's the geometric series, right? When does this converge? When the absolute value of this is smaller than 1, right? Well, we can take off the absolute value because x squared half is always positive, right? Or 0. So what we have is this. So that means x squared is smaller than 2. So the absolute value of x is smaller than the square root of 2. All right? So this is the condition, right, for the convergence of this. So that means the radius of convergence of this series is the square root of 2. All right? Okay. Let me just write this function in a better way. So what we're going to do is, well, same as we've done in the previous case. So we write the series here, and we write the x to 2n here, and down here we have 2 to the n times 2 to the n plus 1. So 2 to the n plus 1. So that is this is the expansion of this function here, right, with this condition for the convergence. All right. Okay, the last one, the fifth, is this expression here, 1 plus x minus 1 minus x times the exponential of 2x over the exponential of x. And again, there is a sort of a trick here to do this. Is not try to do this in the way it's written, but in a different way, which is simpler. So this is the function, and looking, let me check. 1 plus x, 1 minus x. Yes, right. Okay, the temptation here is, well, you take, you know, the expansion of the exponential, you just multiply by this, simplify that, and you have the exponential here. Why not divide in series? Well, this is a very bad idea. This is a terrible idea, right? Dividing series is something extremely complicated, so don't do that. So the thing is, first of all, try to write this in a better way. Can we do that? Well, actually, yes, because dividing by x is the same as multiplying by e minus x. So actually, what we're doing is, or what we have is this series here. But still, we don't have to multiply series. We can multiply functions, and then we have 1 plus x times e minus x minus 1 minus x e 2x minus x is plus x. This is a much better way to calculate this function, right? Okay, let's do that. And for that, we're going to expand this one, and this one here is the same function with x changed by minus x, right? Actually, we're going to do the opposite. We're going to do this one, right? And this one is the same, changing x by minus x. So let me expand this one. Okay, how do we do this? Well, this is just 1 minus x multiplied by this series from 0 to infinity, x to the n over n factorial, which is the same series, x to the n over n factorial, minus x times this series, which is the sum from 0 to infinity, x to the n plus 1 over n factorial. All right. Let me transform this one in order to have powers of xn rather than xn plus 1. So we copy the first, x to the n over n factorial, and then the second is, well, I shift 1 unit down this one and increase 1 unit this one, so I have the sum from 1 to infinity, xn over n minus 1 factorial. Now we can group these two things together, and we have the sum from 0 to infinity of 1 over n factorial minus 1 over n minus 1 factorial times x to the n, right? Maybe a better way of writing this is to multiply by n up and down, because then we have n factorial in the denominator, and then we will have 1 minus n over n factorial x to the n, which is the same as minus the sum from 0 to infinity of n minus 1 over n factorial x to the n. All right? Okay. Now, as I said, if this is the function, right, what I have now is to calculate this one, simply replacing x by minus x in this expansion here. So what we have is minus the sum from 0 to infinity, n minus 1 over n factorial, and then here I have minus 1 to the n, x to the n, right? Which, of course, you can add here plus 1 and change the sign here, right? Okay, now I have to subtract these two series, right, to get f. So I take this one from 0 to infinity, n minus 1 over n factorial, minus 1 to the n, x to the n, and I subtract this one, and since there is a minus here, then I have to add this series here, from 0 to infinity, n minus 1 over n, x to the n. And we can put these two things together by, oh, by the way, this is plus 1. I forgot this plus 1. We can put these two things together just like this, n minus 1 over n factorial. And then I have minus 1 to the n plus 1 plus 1 times x to, there's a factorial here, x to the n. All right? This symbol here we have seen it in another exercise, has two values depending on the parity of n. If n is odd, then this is even, and therefore this is 1, so then the total of this sum is 2. If n is even, then this sum is 0, because if n is even, this is odd, and therefore this is -1, -1 plus 1 is 0. So what this means is that only the odd terms will survive here, and for those terms, this coefficient is going to be just 2. So f of x is equal to the sum from k0 to infinity, right, of 2k plus 1 minus 1, so 2k. I'm just taking the odd numbers, right, only the odd numbers. Then, so this is 2k. Down here I have 2k plus 1 factorial, okay. This is 2, right, so instead of 2k I'm going to write 4. And finally I have x to 2k plus 1. So this is the final form of the series. And of course, the series of the exponential are both, they both converge in R. So the radius of convergence of this one is infinity. So this one converges for all x in R. And that is the last.